Welcome to this evening, and thank you for joining us. This is the University of California Observatories Ask-an-Astronomer virtual event series. I need to let you know that this event is being recorded and it's also being broadcast live on Facebook. So if you don't want to appear in the video, then you can turn your video off. My name is Marianne Campbell. I'm the UCO Communications Specialist, and I'm delighted to announce to you my esteemed colleague, Dr. Paul Lynam. He is our resident astronomer at Lick Observatory, and his personal research interests are mainly extragalactic. For those of you not familiar with our Ask-an-Astronomer series, questions have been collected in advance from our UCO and Lick Observatory social media channels, and also from emails we've received at social@ucolick.org. We've pulled together a list of those questions that we believe we can get through in our 30 minutes. If we do run out of questions, we may ask for additional ones from you, the audience. If you live for the Q&A at the end section at the end of the astronomy lectures, then this is definitely the event for you. Before we start, I just want to thank you for your continued participation in this program and also our Living Room lecture series. We really miss seeing you all in person, especially at our summer series events at Lick Observatory. And we're really appreciative that you continue to share the beginning of the week with us each Monday. So, let's move on to this evening. We have received a fantastic amount of questions this week, and I'm going to begin with a question that we received via Instagram from .cal, and her question was, have we been able to travel to other galaxies, and if so, how does astronomy take part in this? So over to you, Paul.
Okay, so we haven't, well, first of all, welcome everybody, and I hope you're doing well in these COVID era times. As Marianne said, we do really miss your involvement here on the mountain and the community spirit that we experienced during the public event. So hopefully it will all be different this time next year, and we'll see you in person. Regarding whether we're able to, have we been able to travel to other galaxies? Physically, no. But many astronomers like myself would argue, yes, we have, because we're able to travel in our minds, and we're able to use our telescopes to travel to galaxies, to distant galaxies. And we use the medium of the light that those galaxies emit, and we try to analyze and inspect the light that comes to us from those galaxies. Also, we believe that some galaxies are traveling to us. So we're living in the periphery of the spiral disk of the giant Milky Way galaxy. And we think we have signals of smaller galaxies or satellite galaxies around the Milky Way. We call them the Large and Small Magellanic Clouds. At least one of those, and possibly both of them, have been through the disk of our Milky Way galaxy at least one time. So we think that these satellite galaxies, the Large and Small Magellanic Clouds, may be being consumed slowly by the Milky Way itself, and being cannibalized is one of the astronomical terms that we use for this process. So some of the galaxies do indeed.
There are a couple of satellite little galaxy clouds near the Milky Way.
I think I got muted there. So some of these galaxies, like I say, we have evidence that they've been or in the process of being assumed and cannibalized by the Milky Way. And indeed, we also know that our Milky Way itself and another nearby galaxy, the Andromeda galaxy, are gradually falling towards each other. So in about 4.5 billion years or so it's safe to go out and buy a CD and enjoy it, because it's going to be a long time away. But eventually we anticipate they will merge. And it seems that this cannibalization and merging of galaxies during the age of the universe is something not uncommon about galaxies. Okay, I believe Marianne may be continuing to administrate the people entering the room. So I have the next question that's on the list here. And the next question that I have came from an email which was from Sanvi Mokashi, who is a 6-year-old girl extremely interested in astronomy and a Chabot fan. And this was through the medium of Gorang, her dad. And she's trying to get her value for money because she asks 3 questions in one. The first is, which came first, the galaxy or the supermassive black hole at its center? So this is a profound question that many cosmologists are in the process of working on. And the short answer is we don't yet know. In the past few decades, maybe the past 20 years or so, we have gradually evolved to an understanding that somehow the supermassive black holes at the centers of the nearly normal galaxies are related to the size of the parent galaxy themselves. So there is this weird behavior going on where we think, again, nearly all normal large galaxies contain a supermassive black hole at some level in some state. Sometimes that state can be in what we call an active state, and sometimes it can be in a quiescent state. But the mass of the black hole, the supermassive black hole at the center, is somehow related to the size of the galaxy it's in. And the spatial scales are so discrepant that it's a challenge for us to understand how can one scale know about the other and how are they so intertwined. As we use some of our telescopes to look deeper through space and further back effectively in the history of the universe, we see this kind of relationship persist, and we still see evidence of black holes. It turns out, as you look further back in the history of the universe, there is an epoch or an era in the age of the universe where we see more activity from certain types of galaxies in inactive states, and perhaps material falling in around the supermassive black hole at the centers of them. So there seems to be this intimate connection between the presence of a supermassive black hole in the center of a galaxy and the size of the galaxy itself. And this seems to persist at least a significant part way back in the history of the universe as we see it. So trying to understand which came first is a challenge for the present generation of equipment and astronomers and future generations as well. It tells us, by trying to answer that question, we're also trying to answer how galaxies form and evolve over time. And certainly there is evidence for both scenarios. We have evidence for seeing what we call a monolithic creation of a galaxy, a monolithic collapse of large clouds of gas and dust in the early part of the universe's evolution, with sufficient amounts of gas that would make quite a large galaxy today. And in fact, recent results in the past year or two have kind of indicated that this pre-assembled cloud of gas that may be a precursor to a galaxy or proto-galaxy seems to have been observed in place and fully assembled even before our popular ideas of Big Bang cosmology had predicted, some 250 million years after the Big Bang. So we have this, that's one piece of evidence to indicate monolithic collapse of a galaxy from an isolated or single gas cloud. However, we also see these events like galaxy cannibalization and galaxy mergers. And we think we have evidence that at least many of the galaxies in our local universe have experienced those events in the past as well. So smaller galaxies over the history of the universe have combined and spiraled into each other and joined to make larger galaxies. And we also speculate that their morphology, their shape, changes sometimes as a result of these merger events and cannibalizations. So we may have started off with a giant spiral, well-organized galaxy, or a couple of them. They may have merged, and many of our computer models seem to indicate, depending on the relative masses of those galaxies, whether they're going to result in a differently formed galaxy after they've merged together, like a giant elliptical galaxy, for example. Sanvi's next question of the 3 is, when will the universe stop getting bigger? Again, a really profound question. Up until maybe 1998, we were speculating on this because we were thinking we had observed the expansion of the universe from about the 1920s onwards. And one of the assumptions, or one of the things that one of the cottage industries in astronomy was trying to measure the rate at which it was expanding and whether it was going to slow down. We kind of had three potential outcomes, which was the universe would gradually come to a asymptotic stop, and it would just be every particle in the universe would be equidistant, and you get this slow heat death. Or the universe could eventually collapse in on itself, and that was one of the assumptions, you know, that all the mass inside, the gravity within inside the expanding universe would eventually halt the expansion and then cause it to turn around and pull it back in on itself, creating what was then called a big crunch. But since 1998, a couple of very important discoveries were made using supernovae, exploding stars, a particular type of supernova, which indicated that the rate of expansion of the universe, which had previously been assumed to be slowing down, was in fact expanding at an ever accelerating rate. So that was a bit of a revelation. We had to create all these new forces or new ideas. One of them is dark energy, to try and explain this. So if this continues at this rate, we're basically looking at the universe accelerating and expanding ever faster until every particle in the universe continues to be equidistant from the other. So the answer to the question, when will the universe stop getting bigger, is, I don't think, the honest answer is I don't know, and I don't think it ever will, given what we know right now and our current understanding. And Sanvi's third question is quite an interesting one. Why do stars not have colours like green and purple? So this is quite an interesting one, because the thing that dictates the colour of a star primarily is its surface temperature, or its effective temperature. So while our sun, in the middle, in the centre of the sun, it's like 15 million degrees. At the surface of the sun, the temperature is only about 5,000 or 6,000 degrees, and we get this characteristic yellow colour. There are some stars that are cooler than our sun, and they can have a red glow to them. And there are some stars that are hotter, maybe 10,000 degrees or so, and they can appear white or bluish. But this is only in the visible part of the electromagnetic spectrum that we are used to working with as humans. And we have evolved with our eyes to be tuned primarily to the visible light, and particularly the yellow part. We're sensitive to the yellow part that corresponds to the light being given off by the sun. And our sensitivity, our eye sensitivity, cuts off at the red and blue ends of this rainbow spectrum Richard of York gave battle in vain. So we tend to see the cooler stars as red because we're not able to see the overlapping colours on longer than the red wavelengths. And similarly on the blue or purple end, we're not able to visually detect with our eyes the overlapping colours beyond the blue and the red when you go to the ultraviolet. And the peak of the output of the light, dependent on the temperature or the colour of the star, is not just a very narrow colour, but it's actually spread over many colours. So even though we may have stars that their true colour peaks in the bluish part of the spectrum, the shorter wavelengths, more blue than the visible blue, are cut off, and the longer wavelengths, longer than the blue, towards the yellows and so on, they are also included. So it kind of moderates our perception of the colour of the star. So that's why we broadly see cool stars as red, medium stars as yellow, and then the hotter stars maybe as a white or blue. But it may not be quite true that all stars don't have colours like green. I have heard tell that there are a handful of stars in the sky that when you look at them with a telescope or with your eye, some people claim to perceive a greenish tint to them. And one of those is one of my favourite stars. It's got a funny name. It's called Zubin al-Ganubi. And it's a star in the constellation of Libra or Scorpio. It's on the border of the two. And you can probably still catch it in the early part of the evening tonight if you look at it with binoculars. And I'll leave it for Sanvi to decide whether she sees a greenish tint to it or not. But looking at the night sky can sometimes be a little bit underwhelming, because when you look at these great pictures from the Hubble Space Telescope, you see all the colour. And when you try looking at certain objects with your eye or the telescope, it can be sometimes quite difficult to discern colour. So have no fear, even if you're not able to see that Zuben al-Ghanubi is a green star, there are other things that you can see with a telescope or a good pair of binoculars that will have colour. For example, the planets Uranus and Neptune, they have very characteristic colours, a blue and a green colour. Sometimes if you're lucky enough to see a comet, comets can have this kind of lurid, faint green glow about them. Certainly, just with your naked eye, sometimes during a meteor shower, you see these vivid colours. And so on. So be of good heart. You can still see colour in certain circumstances in astronomical objects.
So Paul, I have a question from another Paul Stengel. And his first question is, while years behind schedule and a price tag of 10 billion, the James Webb Space Telegraph will hopefully launch in March 2021. What are some of the questions astronomers hope to answer, and what discoveries might be made with this unique space telescope?
So the James Webb Space Telescope is primarily designed to work at wavelengths of light and exploit parts of the electromagnetic spectrum that we are not good, or we don't have the facilities to achieve from ground-based telescopes. So primarily, one of the clues actually is if you look at the pictures of the James Webb Space Telescope, you'll notice that the mirror segments have a characteristic gold colour to them. And that's because gold is a more efficient reflector of infrared light. Now, from the ground, infrared observations can be hampered by the atmosphere primarily and the water vapour in the atmosphere. So very close to the visible light, we can do something, and we do some infrared observations here at Mount Hamilton. But as you go to longer and longer wavelengths, the atmosphere itself can start to emit and swamp out the data that we collect. And sometimes there's only a few windows that the atmosphere allows infrared light to transmit through the ground. So the atmosphere causes a problem. So one of the advantages of a space telescope, like the James Webb Space Telescope, is to get out of the atmosphere and avoid that infrared radiated blanket that swamps all the ground-based infrared astronomy. So the James Webb Telescope itself, hopefully, is going to give us that access to those infrared observations. And it's not just taking advantage that we can get into space, but there are astronomical reasons for us to want to work in the infrared. So there are very red objects, for example, very high redshift, very distant objects that have been coloured even further into the infrared by the nature of their riding on the cosmic expansion. So very distant galaxies, these proto-galaxies, very near the birth of the universe. And there are very dusty and cool environments that infrared light is able to pass through. So in visible light, we would just see like a curtain of dust in front of these things. So planetary systems potentially in formation, there's gas and dust going on, the dust obscures our visible view, but hopefully infrared observations with JWST will allow us to penetrate those dusty environments and see planetary systems or more planetary systems in formation.
So you covered some of what Jeff Markham, who also had some similar questions, asked during that answer. But one of the questions he also asked is, this is from Jeff Markham, are supermassive black holes the reason galaxies form, or are they a product of them?
In parliamentary terms, I would refer the gentleman to the answer I gave some moments ago regarding how galaxies are assembled and how whether they're monolithic collapse or merged through the history of the universe, and the intimate connection between galaxies and black holes themselves. And the short answer is we don't really know, but we're working on it.
Okay, so Sovan Akaria, and I apologize if I said that incorrectly, sent us a message from India. They are wondering to find an exoplanet, what methods are involved other than the transit method?
Okay, so the TESS is the Transiting Exoplanet Survey Satellite, and that's a successor to the Kepler satellite. Many of the preliminary work and tests were done for Kepler here on Mount Hamilton, the Lick Observatory. So clearly Sovan is aware of the transit method. The other primary method that is used to detect planets, and the earlier method, is something using Doppler shift. So when you take a spectrum of a source, typically the chemistry of the environment around the source imprints characteristic chemical lines in front of it. And it's almost like a barcode superimposed over the rainbow. of the source itself, and dynamical effects cause that rainbow or that barcode superimposed over the rainbow to move around, depending on whether the source is going towards you or coming away from you. So you get a shift of this pattern towards the blue part of the rainbow if it's coming towards you, and towards the red part as it's going away from you. And if you see this regular oscillation in these spectral lines, they're called, then that tells you that there's a periodicity. So primarily we can examine stars and see how those lines are shifting red, blue, and that's indicative that something is pulling the parent star along the line of sight to the telescope. And this is this Doppler motion. This is a wobble induced in the planet by the massive, in the parent star by the massive planet orbiting around it gravitationally. So that's the transit technique, and then the Doppler technique. I'm also aware of a couple more techniques that have been road tested, at least here at Lick Observatory. One is using a very specialized mask that you can place over the telescope aperture. Amateur astronomers may be aware of things like Batinoff masks and Jacques Hartmann masks and so on. We can do something akin to that by placing it over a telescope here at Mount Hamilton, and any positional shift, tiny astrometric shift of a star in position on the sky due to a wobble induced by a planet going around it may be detectable by the way the diffraction pattern changes in the image produced by the mask. I'm not aware of any positive detection yet, but I know tests have been performed here. And the other fourth technique that I'm aware of, again, that's been tested, I'm not sure if it's actually been used to detect an exoplanet yet, is using, is a very interesting technique, using polarized light. So if a star is emitting light and it's a fairly clean environment around it, typically the light that comes out is not polarized. If it happens to have a planet with a cloud deck going around it, then the light, some of the light coming off the star will hit the clouds, and that will introduce a polarization effect in the reflected light off the cloud decks of the companion planet. And there are techniques available where we can distinguish between, if we look at the star from a great distance, even though the star and planet light are combined, if you were just to look as a point source almost, we can use devices inside our cameras or instruments to separate out the polarized light and the unpolarized light, so the reflected light. And although the unpolarized light is vastly the majority of the light that's coming out, we can probably have a technique to remove that. So we're only left with seeing the polarized light from the cloud decks of the companion planet. And one of the powerful outcomes of this technique, if we can get it to work, is that potentially as a planet orbits its parent star, it may go through phases, just like the moon and Venus go through phases when we observe them from Earth. So the amount of polarized light that we see may change on a periodic basis. And this is one of the techniques that gives us, it answers one of the questions I think that Morali has asked in relation to these exoplanet detections, by being able to interpret the changing amount of polarized reflected light from the companion planet by watching it orbit or determining its orbit. We may be able to determine the inclination of the system, which is one of the things that has been very difficult to find for most of our planet detections because we don't have enough information.
Okay, so next up we have a question from Harold. He was the VC Emeritus Business and Finance. He has asked a couple of questions. The first one is, I'm interested in other planets and their moons and how they rotate, such as clockwise or counterclockwise. Do they also go around their sun? Does gravity influence their rotation?
Gravity certainly influences their rotation. In the solar system, and there is a health warning here, I must tell you that our solar system is not the best analog for every other solar system that we are exploring or detecting, the many thousands of exoplanet solar systems we have now. But in our solar system, the convention is to assume you're looking down on the north pole of the sun, and nearly all of the planets, or all of the planets, orbit in a counterclockwise direction, anti-clockwise around the sun. Also, most of the moons of those planets do the same thing, with the exception of the outer moons of larger planets like Jupiter and Saturn and so on. one big exception is the largest moon of Neptune, called Triton, which rotates in the opposite direction. And another exception is Uranus, the planet Uranus, which is canted over almost 90 degrees from its orbital plane. It's almost like something hit it millennia ago and toppled it over, so that the south pole of Uranus virtually points at the sun. Now, the planets are all held in their orbits, and the moons are all held in their orbit by this dominant force gravity on these distant scales. And they're captive, and the various lining ups and repetitious lineups of the planets, the sun, and so on, the larger planets like Jupiter have greater effect, can cause what are called resonances on all of the objects in the solar system. So, for example, around Earth, or leading and trailing Earth, we have a collection of asteroids which occupy the orbit and lead Earth around and trail Earth by 1/6 of the orbit. And those are called Apollo asteroids. Same thing for Mars. Mars has trailing and leading asteroids called Amor asteroids. We know that meteoroids trails and meteoroid streams are also chopped up and governed by the gravitational effect of the more massive planets in our solar system. So yeah, gravity and these gravitational resonances do influence the planets and how they revolve. Another interesting thing that I only learned a few weeks ago was that the planet Venus, because of a gravitational resonance with Earth, it presents always the same face to Earth when it's closest to us. And I can recommend a website called Astronomy Picture of the Day, and it has within the past month, has a beautiful animation of this effect of Venus always presenting its face to Earth. And that's, again, the result of long-term gravitational resonance and tidal effects.
Okay, so we're coming up to 4:30 now, Paul. So, and I've also had a few questions come through on the group chat that I'd like us to get to. So I'm going to move on to Nick Hervey, whose question came from Instagram, and the question is, how were the continents on Venus and you can correct me if I say this wrong, Valles Marineris on Mars created, since those planets lack plate tectonics?
Okay, I'm not sure whether it's true to say they lack plate tectonics. One of these is very close to my heart, actually. If we look at radar maps of Venus, and if we look at Mars, for example, we see features that we think are characteristic of geologic activity, plate tectonics, and volcanism. So maybe not right now in Venus's case, but we still see mountains and rift valleys and mountain ridges that are telltale signs of plate tectonic activity, continental drift, as it used to be called. So I'm not sure whether we can actually say definitively that they lack plate tectonics. And I know for certain that Mars still has, we believe, some low-level volcanism. Because one of the results of volcanism is the gas methane. And I actually helped assist an astronomer to detect methane emerging from the surface of Mars a few years ago using a telescope in Chile. So I think we cannot definitively say that there are no plate tectonics or geologic activity on those planets.
Okay, thanks for that, Paul. So next up we have a question from Marianne Huffacker, and she says, do you have a favorite or just quirky astronomer from the past, and what do you find interesting about him or her?
There are many.
It's being recorded.
Yeah, I have to change names. There are many, depending on your perspective. So I'm from a small island in the western coast of Europe. So the first famous astronomers that I was aware of were Irish astronomers, people who built the largest telescopes in the world many times over. One of the most famous ones is Lord Rosse. He built the largest telescope in the world in the 1840s. Discovered the spiral structure of galaxies, for example. Also, people like Edward Barnard, who came from a poverty-stricken background and became a very famous astronomer just through pure grit, determination, and dedication. I would have to include maybe on the periphery, the observatory's founder, James Lick. We all have our quirks, I think, but James Lick had some very particular characteristics. But from his interest in astronomy and what he gave to the world with this observatory, and the things that this observatory has contributed, I think James Lick can be honoured, and he had an amazing life story, if you ever get the chance to learn about it. And from my personal past, I would have to say, anybody who ever gave me an assist or allowed me to look through a telescope, I've always admired and been grateful for those kind of opportunities. Looking through the telescope for the first time is something you'll never forget for as long as you live.
That's a great answer. Thank you for that, Paul. And so now I'm going to ask you a question from Oliver, and he's age 10. And he wants to know, do black holes expand when they suck in matter?
Oh, I think this is a common question. I think this question was asked in some form with Matthew Chitrone, our Deputy Director, last week or a couple of weeks ago. And the answer is yes, in a way. So we don't know if they physically expand. They just get more massive by that amount. And we have some kind of mathematical description of a black hole. And as it gets more massive, something called the event horizon gradually moves further and further out. So the point itself doesn't get any physically bigger because it's just a singularity in space-time. But we would believe that as matter falls into the black hole, the mass of the black hole itself does increase, and then the event horizon of that black hole expands in proportion to the mass of whatever the singularity is at the center.
Okay, so Paul, I'm going to put you on the spot now, and I'm going to ask you some questions that came into the group chat. So you'll have to think on your feet. So the first one is from Al Smith, and he says, dark stars have been suggested in the very early universe, stars formed with dark matter and growing to immense size. Obviously, this probably requires a speculative leap in the properties of dark matter. But if dark matter has gravity and perhaps low interaction, why would it not form extremely massive objects in the very early universe and collapse immediately into supermassive black holes along with baryonic matter?
Right, so I actually missed the initial couple of words. Was it dark spots have been seen?
Dark stars have been suggested in the very early universe, stars formed with dark matter.
Dark stars.
Yeah.
Okay. Yeah, so I think we already have trouble trying to understand and identify and isolate and detect what dark matter is itself. We're still only really at the level of trying to describe its properties. What we think we know is that dark matter, although it has a gravitational effect, it does not interact with what we would consider normal matter in the ways that we would intuitively expect. So whereas normal matter seems to move around the universe in a particular way, what we infer from our observations is that dark matter doesn't necessarily follow the same material or interact. So, for example, if you throw two lumps of dark matter together, they don't necessarily form shock fronts, as you say, as two clouds of gas colliding you would expect from. Or if you had two balls of dark matter and you threw them together, they wouldn't bounce off each other. They have this weird, dark matter appears, from what we know so far, has a weird behavior about it. One of the great demonstrations or great illustrations of how gas, normal matter and dark matter seem to behave differently is in something called the bullet cluster, and I would recommend Al to maybe try and Google a picture of the bullet cluster, which shows these three different elements behaving in slightly different ways over slightly different timescales, which kind of illustrates that dark matter doesn't really form and bind together in the same way. One of the phrases that we used, or one of the characteristics we think we have for dark matter is it's collisionless.
Okay, thank you for that. So here's another one. This one is from June, and she says, could you explain 4D space-time and perhaps the fundamentals of general and special relativity?
Okay, that's a big question. So 4D space-time, the simple way to think about it is, I think hopefully June is familiar with the idea of 3D space, and you just simply add time to that, and they're locked together. Space and time are locked together. So that's how my concept of 4D space-time works, although you will find some astronomers who will advocate that there may be 66 dimensions of space-time, and many of them are compactified. But the idea is that when the universe was born in the Big Bang, both space and time were created. So there was no before the Big Bang, because time was not created. So space and time, the 3 dimensions of space and the time dimension, are locked together in our experience. The other one was explain special and general relativity. Well, special relativity was a special form of general relativity, and general relativity came a bit later. But basically, general relativity tries to describe, it's a description of gravity, basically, and how things move in curved space-time, in this space-time scenario. So heavy objects seem to introduce curves in space-time, and then objects and light, in fact, seem to follow straight paths in that curved space-time. And this has become our most popular and best description of how gravity works. So this came from some of the work that Albert Einstein did, and it has kind of superseded the work that Isaac Newton did, but in everyday experience, general relativity just does reduce down to what we learned at school. One of the experiences that most students have when they go to study astronomy and gravity in university is they go through this event where their professors at university suddenly say everything you learned about Newton at school you can throw out the window. You know, there is no force of gravity, it's just curved space-time. And it's a horrific experience for some of us that we have to throw away everything we learned before. So the space-time and general relativity is just our best available description of gravity right now.
Oh, well answered. Thank you for that. So this one is hopefully a little bit simpler and more theoretical. So Elsa is asking, what is beyond the universe? What do you think is beyond the universe?
That's a really difficult one. So I'm going to stay within our own universe, because that's what I would argue I'm most familiar with. But I know that there are some of my colleagues and theoretical colleagues who try to work on the idea of multiple universes and membranes and brain worlds and so on. And the idea that there may be, when these membranes collide in this multi-dimensional space that I mentioned, this 66-dimensional space, that may cause events like other Big Bangs or even our own Big Bang. So for me, it's going a bit beyond my understanding of physics and mathematics to talk about other universes beyond our own, although I know there are discussions and speculations about these other universes beyond our own in a multiverse of universes.
Okay, so I'm going to make this the last one because we're coming up to 4:45. And this is from Owen, and it says, do you agree with the assertion that predictions of Planet 9 are due to observational bias at the observatories that are involved in the detection of Kuiper objects?
I haven't seen the arguments for that assertion. I know that there are many programs around the world that are looking for purported Planet 9. And when I grew up, we did have Planet 9. It was called Pluto, and Pluto is the archetype of the Kuiper belt objects. And by virtue of those searches, we are finding hundreds, probably, of these minor bodies in the outer part of the solar system. I'm not familiar with all the arguments about whether it's observational bias in this particular search for Planet 9, but I would say that examination of biases and uncertainties in scientific data is always subject to scrutiny, and very often people can overestimate the account they have taken their uncertainties, only to be found later on that they relax the errors and uncertainties that are introduced in the data. So it may be right and it's scientific procedure to examine those uncertainties, but I'm not familiar with all the arguments. Another famous topical case of this is the present called cosmic tension between our measurements of the age and the expansion of the universe and so on through comparing various different measurements by various different means. So the devil is in the details sometimes in terms of the uncertainties that astronomers quote with these things.
Okay, well, thank you so much, Paul. I hope you've enjoyed today as much as our audience have. Everybody, we're at the end now of our session for Ask an Astronomer. I want to thank you again on behalf of all of UC Observatories for joining us. Next week, we will return again with another living room lecture, this time from Andrea Getz of UCLA. She will be giving a 30-minute lecture about using and developing high spatial resolution imaging techniques to study star formation and investigate the proposed massive black hole at the center of our galaxy. Her lecture will be followed by a 10 to 15-minute round of questions. We hope you will join us then at the same Zoom link that you used today, or on Facebook Live on the UC Observatory's Facebook page. In the meantime, have a wonderful rest of your week and keep sending in your questions for future Ask an Astronomer events. Thank you so much for joining us today. Good evening.